divisions include technical staffing, that's obviously my focus. We also have finance and executive staffing, and we have recruiting for medical related people as well. We have many other sponsors like Utah Geek Events. We have partners like the state of Utah and their different divisions that are all helping us to work on this air quality competition and other things going forward as well. So I'll let Pat take over from here and make some additional introductions, and then keep my mouth closed for a minute.
So hopefully everyone's been finding the data. We announced on Friday we got a lot of JIRA tickets up there. There's a lot of links to data. Hopefully with this time off, we're here this week, but we're not going to be here on Friday, so hopefully you're spending some of that time collecting some of those data sets, starting to play with it, trying to figure things out and learn. And then we're working on right now in July, mid-July or so, to hopefully have some actual computing resources for you to use. This may be a cluster out there that you're going to connect to. This may be AWS services that you can use, something else, but the idea is giving you some computing power to actually do some of this work. Now, one of the questions that came up to us was, are we doing a certain schema or a certain design for this sort of thing, and do we have to use Hadoop? No. You can use whatever tool you want. To clean the data and to get it ready, we don't care what you use. Even when it comes down to analyzing the data later on, we're not going to tell you what tool to use. This is about big data and any tool that you want to use to make that successful. We're not limiting you to one certain space or one certain thing. So please feel free to use any tool you want to try to work on the data, whatever you're most comfortable with. We do suggest that you try to learn and you do a new tool. That would be great. This is the sort of project you want to learn on, and you can get lots of resources from other people. But it's by no means required for the competition, for anything we're doing today. Okay? Any quick questions about overall any JIRA tickets you're having issues with? Somebody asked if we can turn on comments. We did turn on comments. The only thing we ask there is don't let them go too far. We don't want novels in there. We don't want millions and millions of comments in there on JIRA, but we do want the comments. So we have turned it on. If you have an account, you'll be able to make comments. Okay? Any other questions general about the air quality right now before Bryce gets started?
What should we be doing over the next 10 days?
What you should be doing over the next 10 days is going to those data set links that are in the JIRA tickets, trying to get data, pulling that data down locally, playing around with it, starting to clean it, and then discuss with other people. If you run into a roadblock, please use the Google Groups. Please. That's the best place to ask the question. If you send it to Nick or myself, we will happily respond, but we want the whole community to get that information, not just us, okay? And we'll make sure that some of our experts are looking at those Google Groups as well to say, help out with those problems, okay? Other questions? No? Oh, did you mention, thank you WCF for hosting us today. Brandon's here. Excellent location. Very thankful for that. Come around applause. Okay, we'll have Bryce come up and talk about air quality. He's with the Division of Air Quality. I'm not going to go into all your details or all the different things you do, Bryce, because you'll explain it a lot better than I will. So, thank you.
So first of all, thank you for taking on this project. We, of course, focus on air quality and look at data with our blinders on, and I'll talk a little bit about that today. And really, I don't want to try to focus you too much on what you should look at. I'm just going to give a quick overview of some of the things that we're doing right now, some of the focuses that we have, and why we do what we do. This is a typical winter inversion day, and this should be familiar to anyone that skis. Down in the valley floor, we have the air pollution that gets trapped there when we have these persistent cold pools. Once you get above the valley floors during the winter, the air quality is actually excellent. That provides us some unique challenges. One is that we all live at the valley floor, and most of our industry is focused here. Of course, most of our transportation is focused there as well. The other challenge is that clearly we can't blame anybody else. That once the lid is on the valley, it's everything that we generate and put under that inversion that is stuck with us until the next storm comes and clears it out. This picture focuses that as well. It is unique for Utah. Go ahead.
Can we get the lights? Yeah. Brandon, I was just going to ask that.
Okay.
I think there might be a button there.
There's lots of buttons.
Yeah. No problem.
So Utah is unique in some respects, and actually it's unique in a lot of respects, but when we talk about air quality, it's unique in that we are subject to these persistent cold pools that are over our population centers. There's very few places, certainly in the United States, there are a few places in the world that have similar meteorology and topography, but we have about 2 million people that are trapped under that inversion when they form. And they can persist up to weeks at a time. Because of our latitude, some of the storms that dump the snow on the ground, set up the conditions for the inversions to form, then the storms will miss us for several days or up to weeks at a time. And again, once that lid is on the valley, it persists until a storm comes and clears it out. There's some other unique challenges in Utah as well. Even though when you look at Utah, we're a great big square state, there should be plenty of room, but we are very constrained in the state of Utah. The map there on the right, sorry, my right, your left, looks at land ownership. That even though Utah is a large state, only in those wide areas can we actually grow in. The federal government owns the majority of the state and really constrains what we can do. The other constraint that we have is the topography. That even though some of those wide areas look like we have plenty of space to grow, there may be a mountain or a wetland, something like that really constrains our growth. So in fact, we're actually one of the most urbanized states in the country. And that is that most of our population lives within very confined city areas. When we look at air quality regulations, there's really 4 key components I want to focus on. The emissions. And so air pollution wouldn't be a problem if we didn't have something generating those emissions. Once they're in the air, they interact in the atmosphere, and there's chemical reactions that go on. There's meteorology that traps it, as I mentioned, and then there's topography that concentrates it as well. Next is the population exposure. Again, with those first 2 factors, air pollution wouldn't be a challenge, except that it impacts people. And we know from large population studies around the country that we have increased hospitalization during high air pollution episodes. We have increased asthma medication usage. And when you look at long-term trends, we see life expectancy decreasing in areas that are subject to high air pollution. This population exposure one is interesting for us because we also have been the subject of a lot of those big population studies. That a lot of the initial work at identifying the health impacts of fine particulate matter actually originated here in Utah. And it's because, like that first slide focused, that we have very good air quality the majority of the time. And so there's really good on-off studies that can be done looking at when we have air pollution episodes and when we don't, and then seeing those differences, and they are profound. The next focus that we have is, well, what can you do about it? When we look at sources of air pollution, there's always something that can be done to reduce that, either by eliminating the source. For vehicles, for instance, motor vehicles, we see that catalytic converters and technology have come into play that reduce the emissions that come. Even though they're doing the same work, we're actually driving more miles than we ever have, but air pollution from vehicles is going down because there's technology that can be put in place. And that's true for any of the source categories that we deal with. But there's new technologies. When you look at power plants now, most of what you see at a large power generating station is the air pollution controls. The boiler and the turbine are actually very small, but the baghouses, the precipitators, things like that are looking at controlling the emissions actually make up the majority of those facilities, and that's true for a number of other large polluting facilities as well. Then once you have the controls in place, then you can reduce those emissions. They interact with the atmosphere, and so this circle keeps going around. And the policies that are in place originate at both the state and federal level, determining what level of emissions are acceptable, what population exposure is there, and then the standards are set to protect that population exposure. The Federal Environmental Protection Agency, as directed by the Clean Air Act, is responsible for setting the national ambient air quality standards. And these standards are in place and reevaluated periodically in order to protect the sensitive portion of the population with an adequate margin of safety. And so I know in some of the past discussions we've talked about the different pollutants. The ones we're focused on for the criteria pollutants, these national ambient air quality standards, are carbon monoxide, a process of any combustion, especially if it's an inefficient combustion. The standard for lead. Of course, that's mostly from leaded gasoline, but we still have set sources for mining and other things that emit lead today. Nitrogen dioxide is really one of those that is a key indicator of air pollution. Nitrogen dioxide in itself is actually just a byproduct of combustion in ambient air. Of course, 80% of our atmosphere that we breathe is nitrogen. Whenever we have a combustion process with that ambient nitrogen, it can then be oxidized as part of that combustion process and form nitrogen dioxide. And that's an important chemical in itself, but it also is a precursor to the formation of particles and the formation of ozone. Particulate matter, I've got some future slides to talk about this, but these are just particles in the air. And then the 10 and the 2.5 talk about the aerometric diameter of those particles. And so the PM2.5 particles are those very smallest particles that can evade the body's natural defenses and interact in the deepest levels of the lungs. Ozone is the next one that is a very common pollutant. Until about 5 years ago, was really a summertime issue in large urban areas. But we're finding now that some areas, especially the Uinta Basin here in Utah, are subject to winter ozone as well. And that's some unique chemistry that's going on there that is being studied as much as we can to understand right now. Then sulfur dioxide, basically that's mostly coming from mining and other combustion processes. When petroleum or carbon resources form under the ground, sulfur is trapped in there with them, and so sulfur dioxide is a byproduct of combustion of any one of those fuels. As the standards are developed, there's both a level of the standard and a form of the standard. And so the current standards are there listed, and then the colors represent when those were last revised. And so recently, in 2006, the standard for 24-hour PM2.5 was modified. In 2008, the ozone standard was modified. In 2010, nitrogen dioxide and sulfur dioxide was revised. And in 2012, the annual standard for fine particulate matter was changed. So it's always a moving target. We're always understanding more of the impacts of air pollution, and we're always getting new targets that we have to develop plans then to address. How we analyze or monitor for those pollutants is through an air monitoring network. So historically, throughout the state, there's actually been over 100 sites that we have monitored at times. We currently have about 24 stations that are up and operating right now and looking at population-based ambient air quality. As you're going to be looking at the data sets, this will be a challenge for you because these are discrete points in the valley. And so if you're looking at overlaying that with zip codes or census tracts, you'll find that very often you won't find the monitor in every census tract, for instance. And so you'll have to be doing some extrapolating, doing some least square modeling to look at those impacts and how they may relate to each other. And of course, with particulate matter in particular, those are also elevation based as well. And so if you go up in elevation, a representative monitor may not be available for that data set.
Just wondering on the data that you collect and we're getting access to, what's the incremental time frame? Is it every minute? Do we just get the average based on those other averaging standards? Or
so the question was, I need to repeat it for the broadcast here. The data we collect is in most cases minute data that is then compiled to the form of the standard. And so if it's a 24-hour standard, often what we report to the public is the 24-hour number. If it's a filter-based, it's actually a filter that's run from midnight to midnight. So in that case, we'd only have the 24-hour number for that. For most of the gaseous pollutants, we collect minute-by-minute data that we maintain. The two web references that are here on the bottom, and hopefully they're on the broadcast as well, so you can pause it. Our air monitoring network is revised on an annual basis, really. And so our current network plan is available at that link that talks about every site, what is monitored at that site, what the frequency is, and again, what pollutants are there. And then the next site there, from that information, you can go to EPA's air data site and pull down that information for each one of those monitors. And we often get the question, well, why don't we just maintain our own data? Why do we upload it to EPA? We do maintain our own, but it is in the raw form. And so we'll have spans in there. We'll have problems with a piece of equipment that we keep in our data because we need that. But every year we certify our final data, and then that is put into an EPA repository that then is available to the public. And those can be, again, for gaseous pollutants, that's the minute data that's available. For the particles, it's whatever. If we have real-time monitor, that's available. But if it's a daily filter, only that is available. That really is the best source of the quality assured final air monitoring data. When an area is exceeding a federal standard, we're then go through a process of being designated as a non-attainment area. So these are the current non-attainment and maintenance areas, so past non-attainment areas here in the state of Utah. And Utah is not unique. When you look across the country, pretty much every large metropolitan area has a problem with air pollution. We have some unique challenges because of the topography that I mentioned, but whenever you get lots of people living together, all those sources of emissions combine, and we see air pollution problems. The two pollutants that we focus on are those that we're having trouble meeting that standard. The first is ground level ozone. Ground level ozone, represented there at the bottom of that pathway, is simply 3 oxygen molecules that are forced together by adding energy and reactants that are in the atmosphere. How we control for ozone is controlling those precursors. Of course, we can't control the sunlight, but we can control the emissions of oxides of nitrogen and the volatile organic compounds that then react as part of those chemical formations. Ozone itself is interesting. It doesn't want to be 3 ozone molecules, and that's why it's very reactive. That's why when it impacts your lungs, it's a strong oxidant, and it causes basically a sunburn inside the lungs as that energy is displaced during that reaction. But it reacts on surfaces, and we find that when ozone isn't actively being produced, or when you turn the sunlight off, you see those concentrations dip down rather quickly. And so in the mornings, concentrations are low, they peak in the afternoon, and then in the evenings, they're back low again because of that reactivity. The fine particulate matter that we deal with, and again, our focus is the PM 2.5, so about 1/40th the diameter of human hair. For us, most of that is not just crushed up fine beach sand. So in some areas of the country, the majority of the particles are crustal material. Actually, for us, the majority of the particles are formed in the atmosphere chemically under those inversion conditions. Yes?
So ground level ozone, is that because we live at ground level, or how high up do we consider the elevation of ground level?
So for us, it's basically where we stay. So in Utah, 13,000 feet is the highest we can go. And so ground level ozone is focused in that area. It's interesting, in different parts of the country that's different. When we look at regional transport of ozone, of course, here in the west, we're seeing that at ground level at 4,000 feet. In the east, they may see very high concentrations at 4,000 to 10,000 feet, but of course nobody lives there, so they're focused on the sea level ozone. And because it's a ultraviolet reaction, or ultraviolet energy that's driving the reaction, we see that we have particular challenges at elevation, that we have more ozone formed at elevation than they do at sea level.
All of you mentioned there was combustion of oxygen and everything that creates the nitrogen outside. Is all of that done by just sun? Or are there any other contributing factors that are creating nitrogen outside?
So yeah, for the formation of nitrogen dioxide, it's pretty much just combustion processes. There's some degeneration of ammonia that can form some naturally, but mostly what we deal with when we look at our inventory is combustion sources. So that's the next thing I want to focus on, is when we look at air pollution and those emissions, we look at the sources of those emissions. And so some of the data sets you look at are looking at inventories. And we slice and dice inventories based on the particular need. So when we're looking at a wintertime inversion problem, we're focused on the winter weekday emissions. When we're looking at summer ozone, again, we're focused on those summertime emissions. When we're looking in the Uinta Basin during the winter, we're looking at oil and gas and other emissions that are focused there. But we categorize the emissions in 4 broad categories. The first are the mobile emissions. And that's basically anything with, doesn't even need to have wheels. If it can move, we consider it a mobile source of emissions. So it includes on-road vehicles and non-road vehicles, and some stationary engines that are relocatable. When we talk about area sources, this is pretty much the catch-all. of everything that has to do with population centers and commerce. And so it's everything from residential heating to consumer products that are used in the home, all the way to commercial heating and small industrial processes, food preparation, dry cleaning, things like that. So those are basically population-based emissions. They are directly tied to population centers, and of course, they're a little bit more difficult to control because of that. Point sources are the traditional smokestacks. Those are an easy target because it's a smokestack, you can see those. But here, along the Wasatch Front especially, those are actually the smallest category that we have. So they look like they're huge emitters, but when you look at the fact that the area sources are ubiquitous throughout the area, the mobile sources, of course, are tied to our economy, they overwhelm the point sources. Then the fourth category there are the natural sources. And during our winter inversions, luckily, we don't have to account for much of that. But during the summer and during our ozone seasons, biogenics, and so that's the fact that pine trees actually emit volatile organic compounds. They actually are the largest source of these precursors in our state. And so sagebrush is a large source, and we also see dust sources and fires going into those natural sources. So those all impact our emissions profiles, and those are variable from day to day. When we focus on our winter pollution, and this is a little bit of a busy slide, but again, you can look at it later, what we find is only about 5% of our emissions on a daily basis are particle emissions. But what we find on the filter is those 5% only represent 30% of what we find on the filters. And 70% of the particles actually start out as gaseous precursors. And so in the atmosphere, especially during our inversions, those are converted chemically at various rates to form these particles. And that's one of the challenges that we have of identifying controls to address this, because we have to overwhelmingly control the gaseous component in order to get the benefit on the filters. Again, busy slide, but just to show that when we are not meeting those federal standards, we enter into a process to evaluate what's causing that. So we look at the standards, we use computer models with inputs of the emissions and the chemistry to identify what is causing our pollution problem. Then we can identify controls to reduce those. Those are codified into a state plan, and then from that there are requirements put back on those emission sources, and then a feedback to verify that those are meeting those standards. The reason I bring this up is because we just went through this process, and so we have a lot of good analysis that's been done on lots of data sets for past episodes. And so, go ahead.
So is it all reactionary at this point, or are you able to predict some things in the future?
It's mostly, so most of the chemical modeling work that's been done has been describing past episodes. Then once we have the meteorology, so we can predict what happened in the past, we then use that tool to predict what changing the controls will do in the future. And so we do have the ability to predict years in advance. We don't have maybe the best ability to predict what happens days in advance. The result of this process was an 8,000-page document that documented how we got where we were, and then we identified enough controls to be able to meet the standard in the future, even with the complications of our meteorology and topography and emission sources. Again, this plan is a forward-looking plan, but it does put new controls on. Just to give it an example, just the controls were identified for point sources, those smokestack industries, was about $500 million in new controls. And the result of that is about 4,500 tons per year of reduced emissions from those sources. And so it's costly, but it is a very effective plan.
That's the smokestack, right?
Yes.
Which is the least significant contributor?
Correct.
How much?
So we're taking about 4,500 tons.
And how much did that cost?
About $500 million.
And how much is that going to reduce overall emissions?
From that sector, very little. So the point sources are the purple line, so those $500 million of controls actually just allow them not to grow as much as they would have just as the economy has grown. most of the reductions are coming from the mobile source sector. And those are mainly as a result of the federal fleet standards coming into effect. And so with the new motor vehicles, as older vehicles come off the road, the new ones are so much cleaner that as that cycle continues, that's where we're seeing a majority of our reductions. So you can see, and the scale here is 2010 to 2019. You can see that the ratios change a little bit over that time. Mobile sources, we have the biggest reduction from mobile sources, but they're still going to be the largest source of emissions in the future. And so as you hear us talking about how important strategies to reduce mobile emissions are, they will continue to be in the future. And the other challenge we have is, as I mentioned, with the growth, as we're growing, we're actually, our rate of vehicle miles traveled is growing at twice the rate of population, because all of our new neighborhoods are out in areas without business centers, and so people are driving farther and farther to get to and from work.
Are these bars percentages of the whole, or are these actual measurements that you're thinking, like there will be
these are
100 tons in that year, and then 90 tons the next year, and 80 tons the next year? You know?
Correct. This is tons per day. So this is tons per winter weekday.
So in 2019, the state is projecting to be producing a lot less emissions.
Yes. And then the challenge there as well, and this is one of the quick descriptive things I wanted to make. So most of these are those gaseous emissions. And so we have to reduce those because it's not a one-to-one conversion. In some cases, it's like a 4% efficiency. And so even though we're reducing a lot of the gaseous emissions, we're seeing the filters actually only go down by about 10%. So we're removing about 40% of our emissions in the valley, but on the filter we're predicting about a 10% decrease in actual emissions on the ground.
So where does this put us in line with the federal standard?
So this plan puts us in line. So this plan shows that this level of control will meet the standard on an average year, or a year averaged over 3 years in 2019. So this is just that earlier map that I showed. So as we look at, and you look at the impacts of air pollution, I think the first thing is those population centers. That as we squeeze more and more people in, and actually we're projected to double the population along the Wasatch Front in the next 30 years, that's more and more people, that's more vehicle miles traveled, and more importantly, that's more of the area sources, because everyone's going to need a water heater, everyone's going to need cleaning products in their home, dry cleaning, things like that, food preparation. Those are going to be on top of the people that we already have there, again, because we're constrained on where we can move. So as we looked at that future planning, we first looked at the current emission sources and those projections. And so the hashed areas here look at the population centers and the emissions that are associated with population. So that's census tract based information. The green circles are those large point sources. And so based on the tons of annual emissions of those precursors that we focused on, that's the NOx and the volatile organic compounds. Those are again focused in those areas. Then we overlay that with the transportation sector. So we've got information from Department of Transportation about daily vehicle traffic. We have the registration information from Tax Commission about what type of vehicles, what our fleet makeup is. And from that, we can then model the actual contribution from those mobile sources. And then from that, we can produce these computer models that look at all those interactions. So it puts the meteorology in, it puts the topography in, it puts all those emission sources in, and it puts, of course, the inversion in place as well. And then this just looks at that comparison, that if we continue growing as we were in 2019, you can see where we would have been if with the controls we've identified and put in place, you can see that it's less. And this is another thing I want to point out, and I always do whenever I get a chance. This plan, even though it's expensive, it's in place, it's going to show attainment with the standard, we're still going to have inversions. The air is still going to look ugly, but our monitors are going to show us that we're meeting the standard. But to the naked eye, even comparing those two, as you look at those run through the animation, there's not a whole lot of difference. Meeting the standard, we were only about 4 micrograms over the standard, so the plan to meet the standard, that 10% reduction, again, is huge for us. It checks the EPA box, but the general public will still see cruddy air whenever we have an inversion in place.
But basically, that's the outcome is going to be the effect of an externality, improved emission standards on automobiles that we don't really have anything to do with. Is that correct?
That is, but the other thing that that really drives that vehicle emissions reduction is also the infrastructure that we put in place here. So when I-15 core in Utah County was completed, that was actually an emissions reduction project. By eliminating gridlock on the freeways, we actually reduce emissions because the most efficient vehicle emissions profile comes when it's operating at a steady speed. When you're stopping and starting, that's when the emissions really go up. And so it also reflects our transportation planning. It reflects UTA's build out of the heavy rail system and the bus system that's in place now. So those are also reflected there as well.
Hawthorne, is that the name of the monitor at the elementary school?
Yes, that's 7th East and 17th South. That's the Hawthorne monitor, yes.
So this 2019 model gets us back to where we were at when?
Never. We actually, we've been monitoring in the Salt Lake Valley since 1958, and the air quality is better today than it's ever been. And that's another challenge for people to grasp. But we have, in fact, I'll show you in a future slide here, some of the recent trends that we have. Yeah, for every pollutant that we monitor, we've seen the trend improving over time. But again, as I mentioned, we're still finding there's impacts from those levels of pollution, so we're always adjusting the bar. And so we're having to meet a more protective standard every few years. But clearly, past planning has been very effective. And when we look at the pollutants we've dealt with in the past, we're seeing concentrations a third or less what we used to see even back in the 80s.
Once we're hopefully below the standards, does that mean that health is going to increase, life expectancy, and all of those things as well?
So yes, the question was, why do we have this goal to meet the standards? And that's because the science says that at this level it is protective. And so we should see, and EPA has published lots of reports about the impacts. And in fact, EPA's look at the latest revisions to the Clean Air Act, the 1990 revisions, through 2010, showed that for every dollar spent on controlling air pollution, there was a $40 return improvements in life and health. And so they've looked at that and said that clearly there is a connection between air pollution and health, and clearly when you reduce the concentrations, we're seeing the improvement in health. So again, to answer look at that question, is it really better today? So here's some of that data that shows that. These are looking at the annual trends for the large particles, PM10, and then our focus on the PM2.5. And you can see those trend lines going in the right direction. That when we look at our maximum daily values, we're better now than we have been. When we look at our annual trends, we're seeing that as well in the data.
So what is it we actually see when the inversion happens? Like, I assume some of this is transparent, we just can't see it all, but there's probably a certain segment of this that's actually what we're seeing.
So actually, most of what you see during the inversion is condensed water vapor. It's the fog that you mostly see, and that's what you will see in the future as well. And we've seen days where the days look markedly different, but our filters look the same because we're only capturing that fraction. The other thing is light scatters the most at about 760 nanometers, so at about just less than PM1 is where the most light scattering happens. And so you can have a lot of those really small particles in the air that are scattering a lot of light, but we're not seeing it on the filters. And so again, to look at the health relationship has always been based on the filters, but you will always be able to see it. And water vapor is very effective at scattering light, as are the very smallest particles, less than PM1.
And what is light scattering function?
So that's just the visual impairment. So as you look across the valley, if you can't see the mountains on the other side, most of that is because of the light scattering by small particles in the air.
Not necessarily unhealthy.
Which, correct, is not necessarily unhealthy. I focused on the criteria pollutants, and I will mention just quickly. Sorry, I talked as fast as I could. There are other standards as well. So there's standards for hazardous air pollutants that are beyond this that we focus on as well. There are visibility standards for national parks, for instance. So there's visibility goals. So we're also controlling emissions in order to improve visibility at national parks and things like that. Again, just quickly, as a conclusion, when you look at the data, this is looking at the current standards and comparing past monitoring data to the current standards. And this tells really two stories. One is if you put your hand over 2013, success. We figured this out. We know how to do it. But we know that meteorology can combine and overwhelm any control strategy. So we had very prolonged and pronounced inversions. We had lots of snow on the valley floor. Utah Lake froze last winter. And so because of that, we had some of the highest concentrations we've seen in a while. But it's only been in a while. For those that were here at the Olympics, if you remember, we had about a 17-day inversion leading up to the opening ceremonies. In fact, that year, we had, 45 days that were over the standard that year, whereas as bad as this year was, we were just about 34 days. And so, again, our memory is short, but luckily we can rely on the data to get some of this information.
When we see a huge drop-off next year, can we relate that back to the air quality competition?
Yes, we can. But again, I appreciate your look at this, because we're really focused on what we do. And it's always good to have more eyes and minds thinking about these things and those relationships. So again, that's our quick air quality 101 for here along the Wasatch Front.
All right, we'll quickly switch over. Get Matt.
Well, there's some questions at the end.
Yeah, we'll definitely have time for some more questions. Actually, Bryce, you can answer some right now too if you wanted to. While I'm switching this over, if anybody had some.
How frequent do you have upgrades on the sensors? Or when were those milestones? Is that
I'll be able to.
something of
There'll
interest?
be some stuff that I can align
So
over
they
because
move
you touched
around,
on it
but
already.
basically it's the same method of monitoring that's been in
I
place
can
all along.
focus more on the actual data.
So some of the monitoring stations have moved around as they look for the highest or worst case scenarios. But really the data are comparable over that entire time frame.
And do you add new stations at a period throughout the period?
Nice. Thanks, Pat.
So we're always constrained by budgets. If we had our way, we'd have 100 monitoring stations. Well, I have 1,000 monitoring stations.
Yeah, no worries.
So we're always balancing. Whenever we put a new one in, we also have to take on some out in order to.
The wireless one might be, but make sure I didn't hear him so well. So
Okay, I'll try to speak up.
The models that you were talking about, are those publicly available?
Yeah.
Okay, well, really quick, let's let Matt get started too. They'll both be here afterwards as well, ask a few more questions, so we can chat with them then, and then Bryce can jump in on questions if he needs as well. So I'll give Matt the floor now from MesoWest, University of Utah, and tell us about the data that we have there already from them. Now, this ticket is already in Jira. You can already go out and get this. Matt was the wonderful gentleman that got it all into a nice zip file for us, so it's really easy to get. It's a little large, but it's really easy to get to. So, but that's what we wanted. We wanted the extra data. Yeah. So I'll give Matt the floor to answer all of our questions.
Yeah. So, like Pat said, my name is Matt Lammers. I just finished my master's degree in atmospheric sciences at the University of Utah, and I'm currently a research associate working in the MesoWest group at the University of Utah, and I'll explain a little bit more what that is in a little bit. But I'm just here to talk about the data sets that we've provided to you related to Utah air quality, just give you an overview of what they are, where they came from, what they were generated for, and how best to sort of dig into them effectively. So I'm going to start talking about the Whiteman group data set, which is looking at 40 years of particulate and meteorological data in the Salt Lake Valley. Dr. Whiteman just released got a paper published on this data set in the atmospheric environment, I believe. Then I'll talk a little bit about the University of Utah two-dimensional variational surface analysis, UU2D-VAR. Basically what this provides is hourly gridded 2.5 kilometer analysis of meteorological surface variables over the entire state of Utah going back to January 2012. And then finally, I'll talk about surface observations of atmospheric variables that we aggregate in MesoWest for the state of Utah, which is the big tar.gz file that Pat was mentioning. And I'll talk to you a little bit about how that was created, and then just summarize at the end. So the first data set that we provided is a 10.5 meg tab-separated text file aggregated over the period of 2 years by Dr. David Whiteman's group in the University Utah Department of Atmospheric Sciences. What it contains is meteorological data at 12-hour intervals from the National Weather Service radiosonde soundings, and I'll touch on that a little bit more. Basically, it's weather balloons launched every 12 hours by the forecast office down at the airport. It also includes cloud and snow cover data at 12-hour intervals from the National Weather Service forecast office. over this 40-year period, and then the 24-hour average concentrations of different pollutants measured at different locations in the Salt Lake Valley. A little bit of pretty much overlaps with some of the data sets that Bryce and the Department of Air, Division of Air Quality have given, but it's all in one location. So radiosondes are the payload that is attached to a weather balloon when they launch it. This is an example of a Vice-Oliver radiosonde that's currently used by the National Weather Service. They launch, again, every 12 hours at 0 and 12 UTC at the airport, and it measures air temperature, relative humidity, pressure, wind speed, and direction, usually at about 10-meter intervals as the weather balloon rises, and it's called a radiosonde because it uses radio to report the data back to the forecast office. And what this was used for in the Whiteman data was to get to get these averaged or integrated values over a depth representative of the valley basin. So we're interested not just in what's happening at the surface, but we want to know what's going on in the air all the way up through to the top of the ridge lines. So most of what you'll see in the Whiteman data is actually averaged or integrated values over a column of the sounding, either up to 1,800 meters above mean sea level or about 1,000 feet above the valley floor, or to 2,200 meters or about 2,300 feet above the valley floor mean sea level. Explicit descriptions of each of the variables can be found in the readme.txt that's associated with the file, and also the Whiteman et al. Paper that was just published that we've provided for you guys. There's a lot of variables going on there. The most important one in reading the paper, the one that correlated best with PM 2.5 concentration since 1999, is what's called heat deficit to 2,200 meters. This is an integrated value that says if you have a 1 square meter column that's based on the valley floor and goes all the way up to 2,200 meters, how much do you have to heat that column? How much energy is needed to heat that column to get the potential temperature to be the same that it is all the way up through the column up to 2,200 meters? Potential temperature is an atmospheric science term that basically means if you take that air that's at 2,200 meters and bring it down to the surface, it will heat because the pressure increases on that parcel. The atmospheric pressure increases. So what potential temperature is a sense of, well, okay, if we have this parcel, we bring it down, that's what the temperature would be at the surface. Typically in inversions, the potential temperature is much higher at the top of the inversion than at the surface, and that's what keeps air from mixing through the mixing out into the ambient air, and that's what keeps our pollutants, moisture, things like that trapped in the valley basin. Also, if you were interested in raw sounding data, we didn't provide this to you, but if you're interested in the actual 12-hour soundings, you can find it at the University of Wyoming. They have an archive of all the radiosondes going back decades that have been launched by the National Weather Service, and that's at that address listed down here, weather.uyo.edu/upper air. So moving on to the snow cover and cloud cover data that's in the Whiteman data set. As has been explored, snow cover and cloud cover both promote the development of persistent multi-day inversions during the winter time in the valley. What the Whiteman data contains is that if there is snow cover observed at the airport at 5 in the afternoon on a given day, it's assumed that there's snow cover throughout the valley during the entire day, which makes sense because the airport's near the bottom of the valley. If there's still snow on the ground there, then it's likely to be everywhere else along the valley floor and on the sides of the mountains. Cloud cover is represented as a binary index value. If there's broken, overcast, or obscured clouds with a base below 3,000 feet above the valley floor, so below ridge line, there's a 1. Otherwise, there's a 0. And then finally, we have some pollution data. This goes back to 1973. Bryce addressed what PM 2.5, PM10, and previously there was total suspended particulates before we could get a sense. Technology allowed us to get a sense of what size the particles were. That's what was measured back in the 70s. So this data contains values, 24-hour averaged values for those as observed at different stations of record throughout the valley. These stations of record are shown in this map here, as well as some other Department of Air Quality stations. The total suspended particulate data from the 70s is from the Salt Lake Health Department, HD on the map. PM10 has been measured at North Salt Lake. Hawthorne Elementary is the station of record and has been for PM 2.5 since it was installed. They used the Cottonwood sensor for carbon monoxide in the data set, and then not shown on here but used for carbon dioxide concentrations, there's a sensor run by the University of Utah in Sugar House and also at the U itself. And then all of the meteorological data in the Whiteman data set is taken from KSLC, which is the Salt Lake City Forecast Office near the airport. Three of the main conclusions of the Whiteman paper that are useful to think about, sort of echoing what Bryce said, overall particulate concentrations in Salt Lake Valley have decreased over the last 40 years. He also found the valley heat deficit variable that I talked about correlates well with high PM 2.5 during the strong heat deficit periods. Air can't mix out, winds aloft can't transport the particulate matter out of the valley, and as such the pollutants and moisture are trapped. And then looking at it from a sort of climate perspective, there's no statistically significant trend in stability that can be discerned. What that means is we're not seeing any sort of trend in either increased or decreased persistent inversion episodes in the Salt Lake Valley over the last 40 years. It's sort of random from year to year. It varies. As Bryce showed, 2013 was a really bad year, but the years prior to it had been good, and that's based primarily on. Yeah, go ahead.
Does that explain you had on one of the previous slide you had the 1980s, early 1980s had very low.
Yeah, that was sorry, I should have explained that figure. That figure is actually the count of sampling, like the number of 24-hour average samples. So in the 1980s, there just weren't a lot of total suspended particulate samples that were done during the winter half year, and so that's where that drop-off features up until 86 when they started measuring PM10. So that's what, yeah. But in the bottom in the yellow, if you can see the yellow columns, those are actually the number of samples and exceedance of the national ambient air quality standards at that time. And you can see, if you can see the yellow columns, it was much worse. We were in exceedance much more in the 70s for total suspended particulates than we are currently for PM10 or PM 2.5. So moving on to the UU2D VAR data, this model was developed in 2010 by Dr. Dan Tyndall in collaboration with my advisor, Dr. John Horrell, and later Sha Dong has been keeping that project going. The goal of the UU2D VAR was to assess the impact of surface observations. As an employee of MesoWest, we aggregate a lot of surface observations, and I'll talk about how many that is later. And we want to get a sense of what impact each of those observations has when we compare them to a model-derived background grid. So we get these background grids from the Rapid Refresh model run by the National Center for Environmental Prediction in Boulder. We downscale them to 2.5 kilometers on a grid, and then we run a variational analysis assimilating the surface observations in and then adjusting the model grids based on what those surface observations are telling us the actual observed conditions were. And from that we can get how much change each of those observations does to the model, and by that we can determine the impact of each station. We run it on a CONUS scale, continental U.S. scale. This is just an example from 0 UTC on the 29th for the background grid for temperature. You see it's a hot afternoon in the southwest, cooler in the mountains. So if you watch, when I change from the background to the analysis, you'll see just very subtle differences in the temperature grids. Some places get a little bit warmer, some places are a little bit cooler, and this is all based on assimilating the data from these surface observations. And then if we look at the actual raw values by what's called the innovation, the amount by which the grids were changed, we can get a sense of where the most impactful stations were in terms of how much temperature change they imparted from the background to the analysis. So what we're providing for you guys is these same grids on a Utah regional domain. We've been running this domain since January 2012. Every hour, the files are available as daily HDF5 files, separated into each hour by variable. There's a latitude longitude reference grid on that available on that page as well, called Utah Grids, and that because the grid is on a Lambert conformal projection, you'll need those grids to determine where the actual grid points sit, latitude and longitude wise. We also provided an article on the National UU2D-VAR, Tyndall and Horrell 2013, as well as a PowerPoint presentation on what we're currently using the UU2D-VAR for. We did some work on wind speed, the impact of wind speed observations relative to model wind speed backgrounds of Superstorm Sandy, things like that, how the station observations impacted that. And then we also have a README file on how to read these HDF5 grids in Python, because that's what we use in our department, but it's likely that there are ways to import the HDF5 files in other languages as well. I'm sure there are. The variables for which we have grids available are temperature, dew point, from which you can get relative humidity as well, and then U wind speed, which is the east-west component of wind speed, and then V wind speed, which is the north-south component of wind speed. From that, you can determine overall wind speed and direction as well, if you're interested in that. So these are this is what they look like on the Utah domain for 12 UTC yesterday. On the left you see temperature, center in the middle you have relative humidity, and on the right you have wind. This gives you a sense of what the resolution of this data is. These aren't tiny files. They're relatively sizable, but by giving you just the Utah domain, it helps you guys out. So you don't have to chop it out of the national files that we also have. And then once if you're actually interested in looking through these gridded files, we have a website available so that you can plot the data up using whatever plotting software you prefer to use. We use Python, matplotlib to generate our figures, but you can use this web tool to determine whether what you're doing actually matches up with what we've developed in terms of our visualizations of the data sets. And then finally, looking at the MesoWest stations, MesoWest has been aggregating surface observations for meteorological data since January '97. We started with a tower on the top of the Browning building at the U, and now currently have, as of yesterday, 28,500 active stations for which we're aggregating surface observations. We actually only operate and maintain about 8 stations, but we have agreements with many other organizations that allow public access to their surface observations, and through that we aggregate the data, archive it, and things like that. These stations report anywhere from 1 to 32 different meteorological variables at frequencies anywhere from 5 minutes up to once a day, depending on the station. Most of the stations will report values for temperature, relative humidity, wind speed, and direction. Some don't. Some just report things like precipitation that's fallen. Others will report many other variables, things like solar radiation, if that's what you're interested in. We aggregate all of Utah Department of Transportation's road weather stations, so you can get things like road temperature, road condition, things like that. Those are available in the data sets that we gave. There are currently 834 active stations aggregated in MesoWest in the state of Utah. Some of the stations are seasonal, mostly the ski area stations. They tend to shut them off once the ski season's over. Other stations in the archive were deployed in field campaigns, and thus maybe only have a month or two of data, but that could be useful if a lot of our field campaigns happen to occur during winter time inversions, because that's something we like studying. So we'll have other data from those. But most stations, once they're put into the system, they persist and are maintained regularly or irregularly, depending on whose job that is. So in terms of what we've provided for you guys, the observations from all the Utah stations dating back to January 1st, 1987 have been output from our MySQL database into CSV files using the MySQL dump command. They're stored in a big tar.gz archive at this website, and each file is named data_some number. The number corresponds to the station's internal unique ID that we use to get a sense of what station's what. And then you can use the file stationinfo.csv on that page to discover the metadata that corresponds to that numerical station identifier. The metadata includes location, lat long, elevation, station, full station name, and things like that that you can get from that file. There's also another file called variable.csv, and what that does is all of the variables in the database are stored under 4-letter alphanumeric IDs. Sometimes you can figure out what that variable means, and sometimes you can't. So the variable.csv file allows you to get the full name of the variable, as well as what multipliers need to be applied to that value to get it into its native units, as we generally try to store integers in the database. Not always, but generally, and so you need to apply a multiplier to convert it back into its native units. And then what values are reasonable for that variable. All of the data that we provided is pretty much raw. There can be some, yeah, Pat, go ahead.
On the station info CSV,
yeah.
It mentions location. Were any of these portable? So do they change their location?
Yes. Unfortunately, the station info ID is just a snapshot of our current metadata sort of station info page. Some of the stations have moved. If you're interested in whether a station that you're specifically looking at has moved or not in the past, UDOT has a number of portable RAWS portable RWIS stations, road weather stations. Some RAWS stations, which are stations used for fire weather applications, are often moved depending on where they're burning, things like that. If you have a question about whether you feel like you're looking at the data and like this doesn't make sense, all the temperatures are way too cold, let us know, and we have ways of finding what its previous locations were. But most stations generally stay in the same spot throughout their period of record. And then, as I was saying, variable.csv contains what values are reasonable for that variable that we've, as meteorologists have come up with as reasonable range checks, and that's something that will be useful if you're interested in using this data set in order to get rid of really bad data. And then more information can be found in the readme.txt file that we put with this. And this is an example of Fish Lake Snowtell, what these files look like. The date time is in the first column, and then all of the variable names that can be found out in the variable.csv file are listed at the top. You'll notice that how nulls are handled is pretty much just the MySQL standard. And the files for the stations with the longest periods of record contain up to over 1.5 million rows. In some of these files. So WBB, which is the station that's on top of the Browning building that we've had reporting at 5-minute intervals since 1997, has something like 1.6, 1.7 million rows of different variables. So just to recap, talked about the particulates in the Salt Lake Valley, the Whiteman data set, long-term record of particulates and pollutants observed in the Salt Lake Valley, as well as vertically averaged and integrated meteorological indices and things observed from the Salt Lake International Airport soundings. The UU2D-VAR gridded data, which is an hourly analysis of surface meteorological variables on a 2.5-kilometer grid for the period January 2012 to present. And then the MesoWest station data, values of meteorological variables going back to January 1997 for the state of Utah. And that's all I have. Have any questions?
And these two PowerPoints, I've got them on my computer now. I'll throw them into the jury tickets that these are related to. So you'll be able to see them as well, but they're also recorded. So as always, all of our stuff will go up on YouTube right now. But I know some people will want to just look at the PowerPoint. They've asked that before on the YouTube videos to put the PowerPoints up there. I'm working on that. I just got to get these pushed up there. So if you have any questions, feel free to chat or raise your hand right now or whenever you want. But Bryce and Matt will be here for a few more minutes and we can chat about it. Otherwise, hopefully everybody spends some time over the next couple of weeks looking at this data or other data and, getting started on it. Yes?
I have a question about not being a domain expert of weather or air pollution. What would you advise us to look at? What would be interesting? What would you, if you had the time, be?
Well, actually, so I had an extra slide, but I Pat sort of suggested, oh, well, you'll talk about that in August. But things that we've done a lot of research. There are a number of papers on cold pools in the Salt Lake Valley. We also we've been doing some work out in the Uinta Basin on the relationship between meteorology of the Uinta Basin and the winter ozone problem out there. Things that we don't have time to look at, things that I'm curious about personally, is the importance. I'm interested in how air pollution relates to the sources, the other data sets that you have, because I've seen all the meteorological stuff. But I think that's something to think about when you're, depending on what problem you want to look at, is it important to control for certain atmospheric variables or conditions when you're looking at that point sort, like say if you're looking at traffic data or something like that, and how it relates to PM 2.5, it may be important to control for different atmospheric conditions when you're looking at those data sets, trying to compare those data sets in order to filter out periods of when it's really stormy in the winter. You're not going to have accumulation of PM 2.5 during those periods if it's really unsettled. And also another thing that I'm interested personally is whether the atmospheric conditions that are favorable for pollutant concentrations in one part of the state are the same as in other parts of the state. Is it something that we can just say cold pools everywhere? That's the cause, or are there more nuanced things that that play a role in the Salt Lake Valley and the Wasatch Front versus the Uinta Basin, or versus Cache Valley up in Logan? Things like that. That's what I'm interested in, and things to think about when you're trying to come up with ideas of projects and stuff like that.
Bryce, do you have an answer to that question as well?
Yeah, I think what I'm most interested in are those relationships we haven't thought about. So I mentioned we do a lot with our data and traffic, but we haven't looked at employment information. If there's some record from workforce services that talks about some correlation between when people are absent from work or when they have to stay home because their kids are sick. I think there's lots of those correlations that we can look at, but I think it's important to look at in the context of meteorology. There's a lot of studies that came out. There was a recent one that talked about suicide rates in the Salt Lake area and correlated it with PM. But the correlation went away when we had high PM. And so they said during the fall and the spring, it's correlated. It's not correlated when we have these orders of magnitude increases in PM, then the correlation goes away. So that's important to look at some of those things. You shouldn't even look at those data if you're looking for an air pollution correlation. You should be able to take his data sets, subtract out those days where we have inversions in place, and then focus that data. And I think that there are data sets and information out there everywhere. And I'm just excited, like I said, to see what you can find to look at some of those relationships.
And the good news is I've got emails out right now that we're just about to start talking about tax data, so we can get some financial aspect to this as well. I still have a lot of the UDOT information is in our hands. We just have not distributed to the community because we're still working on some of those pieces. But you're going to have all of that very soon. So to correlate these together, you're going to have lots of different pieces to play with. The healthcare one is coming as well. It's getting very close. So it's just a few more, a day, week or so. We're going to get that together, and then you'll be able to start to actually correlate it. The important thing, of course, though, is getting this down, cleaned, and in a place that you're ready to use it, so that you're ready to correlate it to something else when you get that. Because once we give that data out, there will need to be cleaning and stuff done to it as well. So that's why we're trying to get it out as quickly as possible.
Yeah.
Matt, I noticed that your data sets are on the
CHPC
resource.
Yeah.
So when you were at U, did you work with them? And are there other projects that are underway that you're aware of?
I'm not aware of any other projects currently in terms of CHPC. I mean, they generally, CHPC has been good enough to work with the Atmospheric Sciences Department to provide computing resources, web hosting, things like that, and that's why I mean, all of our servers that we use are in CHPC's domain. So that's why those are that's there. I don't currently know about any projects that are in the works, but or that are currently being undertaken. That's what I have. Yeah.
One more question about the HDF5. Is it the HDF?
HDF5. Yeah.
What kind of format is it? Is it described somewhere?
It's a pretty commonly used format. I honestly don't use it that often because I don't deal with these. I don't personally deal with this size of like these types of data sets. I know it works very well with Python and they have very good support for it. And it's much better than previous formats that the atmospheric sciences community has used, like NetCDF and things like that.
Wasn't Chris saying that there was a Python library for it or something?
Yeah, there's a library for HDF5 reading and writing, and it is compatible with PyTables as well, which is another Python library that you can
So
use.
again, that may not be optimal for you if you're not a Python person, but if you are, great. If you're not, good thing to learn maybe.
Mm-hmm.
There should be HDF5 libraries for every.
Yeah, there really should.
It's one of the most common science data formats.
Yeah. Thanks.
It's just a hierarchical data format, and Python Pandas has a really good support for HDF5.
Pandas does. Yeah.
This might be a question for both of you, but how do your stations differ, and then how do you make the choices of where to put the stations when you only have so few that you can actually use?
So they differ. So we have meteorology in our stations. I believe it's connected to MesoWest.
Yep, it is.
But then we also have the actual loop monitors that we're focused on. And so again, there are those discrete locations, and unfortunately, there's not a really great coverage. How we select them is, I talked about a little bit some of the modeling that we do. So we do some coarse modeling to choose where we need to put it, and then we give Bo the chance to go out there and find the spot. And unfortunately, to meet the criteria, there can't be trees, there can't be large source of emissions, and so we find the ideal place to put a monitor is at a school playground.
Yeah.
And so then it's twisting some arms with the school districts to get us to donate to us a part of their playground. Hopefully we provide something in return. But so we identify a need, and then we just go out on the ground and try to find the site that meets the site criteria.
Well, so along the needs lines, like you have one at Rose Park and then one at Hoffman, and distance-wise, they're not that different from each other. But they're very different places from a lot of other perspectives, like where the roads are, where different factories or points are, right? So does that all relate into it as well?
It does, especially for the particles, and I hope you can see that. But once the inversion is in place, we see really uniform concentrations.
Mm-hmm.
So our focus is representing what the broad population is being exposed to. And so again, our model analysis shows that we're catching most of those. With ozone, it's more difficult because it tends to slosh around. There's basically an ozone cell that develops, and then it can move around. So one day, one neighborhood will get it, the next day another neighborhood will get it, the next day it goes over to Tool County and they get it. And so that's some of those, there's really neat meteorological factors that are causing that, but it does tend to be less predictable with PMs.
Since it's invisible, how do you trace that?
Again, just when it hits a monitor.
Yeah.
We have a string of ozone monitors. We can actually see the cloud or as it moves around. As it will, it's kind of like a pinball. We'll just hit the monitor, and then we'll just see it in the next monitor, so we know that it's moving in that direction. So we can see that around the lake and in where the monitors are.
And then we also do what we call some saturation studies as well. So we've got portable ozone monitors that we can set out there and set them out for a summer, for instance, and determine where it's most likely that we're going to find the highest values. And so for the past 3 summers, I think we've been doing those studies. Really some interesting things, looking at the terrain over the mountains as well. So we're seeing the ozone values be high in Salt Lake 1 hour, and then they'd be high at Harley's Canyon the next hour, then they'd be high at Silver Creek Junction the next hour, and then they'd be high at Camas the next hour. So you'd be able to see that relationship as well.
Can you determine the size of these pinballs? Whether it's maybe because it hits a couple monitors at the same time, or
sometimes you can. Sometimes there are discrete hits where one monitor will go up and the rest of them really won't show much. Usually, it's there's there's probably a reaction, and we know there's some sort of reaction in the lake, and so in the morning a lot of the pollutants will push out over the lake and sits there and cooks like it's in an oven, and then in the evening, in the late afternoon, it starts to pull back in, and so you can see that happen. I think there's some pretty good documentation on the effects of ozone creation over the ocean and stuff on coastal cities, and I think we get something similar like that here.
Is there a difference between the Great Salt Lake that's salty and Utah Lake on ozone? And
just the science.
So the general pattern that these pre-laws usually follow, or is it?
Well, the daily pattern is the standard diurnal pattern. It kind of moves down and up, or down in the morning and up in the evening, or
Yeah.
Wait.
Yeah, that's evening. Yeah, at night you definitely
I was just wondering, like, with you have only a couple sensors for the particulate data. Do you guys, with mobile sensors or whatever, do you have a good sense of how much variability there is with the elevation just within the valley? Because obviously, like, you go to Snowbird and it won't be out of the inversion. Like, once you're above the inversion layer, I can imagine a sharp discontinuity in the distribution of particulates. But I'm curious, like, if you're up on the East Bench in Salt Lake, is that dramatically different than, say, like 4,200 feet down the valley?
Absolutely. And then I think it was Dr. Hull and Dr. Silcox did the cold pool inversion study, and they actually did a transect of monitors starting at the valley floor and going out to, I think,
I don't remember. Top of, is it Granger? Might be. I can't remember. And I know they put up one of the transects. Yeah.
Again, you can see that. You can see once you hit that 54 to 5,600 foot level, you see the concentrations just drop all the way up. And
another thing you'll see is especially in shallower inversions, you'll actually see sloshing, where the top of your inversion layer it's like a bowl of water. Like it'll actually, you'll see like high concentration at a point, and then if it sloshes down, it'll almost disappear and then come back. And that's something that we don't have because of the limitations of vertical profiles. It's very hard to get a sense of that going on. I mean, all we really have is models that we've run, but unless you actually have data to verify that your model is doing what's actually physically happening, that's a tough problem.
So you mentioned that your monitors are set up in places so that you can watch what effect it's having on citizens. Are there monitors that are watching sources of the pollutants, like things along the freeways and so on?
So very limited. Those are supposed to be in short term, but we really focus on the inventory side. And so a lot of the modeling we do has that inventory input. So we know based on engineering calculations and then testing at the companies themselves. And so we actually have stat testing information from all those large sources as well, so we know exactly what they're emitting on a daily basis.
So there are stats, but there are also things like taking up stuff out of the air when you're mining at the Wooded Mountain, right? Kennecott or whatever, right? Same thing, or are there monitors there?
So Kennecott actually operates 2 PM monitors around their facility, between them and Copperton, and then the other one is between them and Harriman, to try to catch some of those if it happens. But no, it's mostly done through either dispersion modeling as part of the bidding process, or engineering calculations as part of the bidding process.
Are there certain particulates that only come from certain sources?
Yes. Yeah, there's a profile for each one. Our lead monitors are located because Kennecott's smelter is a large source of lead, or the largest source in the state, I believe. And so we have a lead monitor that's the magnet area trying to match that. But yes, they're all different. Of course, around the refineries, there are large sources of hazardous air pollutants. So we focus on those on the compliance permitting side to make sure that they're meeting those limits.
Do we get a significant amount of pollution from other states? Especially fire or whatever else?
Fire, definitely.
Yes, we do. In fact, for our summer ozone problems, I'm trying to be happy, maybe it's another topic.
Yeah.
Actually, some of our most rural monitors, so one that's located at Great Basin National Park, just over the border in Nevada, and then one that's located at Island of the Sky in Canyonlands National Park. actually see high ozone values. And there's no transportation sources, there's no industry sources around those, but we can follow, actually, some modeling that's been done is showing that even Asia is impacting those. And so there's long-range global transport of precursors and actual emissions as well. And then we see large impacts from fires, as you mentioned, and then we can also see the more local. We can see impact trajectory analysis on high days and see that it went over Los Angeles, then Las Vegas, and then.
So, are there any aggregates that are visible for metro areas of constellation?
Yes. Yeah, so in my presentation, I gave the links to both the inventory side of EPA and the monitoring side of EPA.
Yeah.
So from those, you can pull down across the country.
Okay, I think that's pretty much it for the afternoon. Like I said, they may be here for a few more minutes. I know some people got to go, but thank you guys for coming. If you have any questions, send them to me.
Yeah, no problem. I actually got to head out, but
Yeah, I
if
figured.
you have